Good morning. Thank you, everyone, for coming for my presentation. I want to appreciate the Slag Cement Association for this award, and most especially, I want to appreciate the Indiana Department of Transport for sponsoring this project through the Joint Transport and Research Board. And my professor, Professor Jan Oleg, incidentally, he's here, so I want to thank you for this wonderful privilege and your supervision. My name is AJUONUMA Chibueze Sylvester. I'm a PhD student at Purdue University, working with Dr. Raikan, Professor Jan Oleg, and Professor Ek Kendra. We're here to present an update of our work on practical implementation of internally cured slag cement using superabsorbent polymers. A rundown of our outline, we'll look at the research overview, we'll look at some of the research objective and introduction and some of the research goals and objective, and then we'll look at a little lab experiment we did that preceded our field trial, and we'll look at the field trial for the project, and through it we evaluate the research overview, the methodology where we consider the materials and methods we used, and mixed design. Then we'll proceed with the discussion on the results. And our results, we'll talk about the fresh properties, where we'll look at workability, the slump, and the air content. And I'll proceed to the strength properties, where we'll consider the flexural, tensile, and compressive strength. Then some durability properties of our experiment, where we'll look at scaling resistance, chloride ion penetration, the rate of water absorption, the resistivity and formation factor. Concrete processes is a well-known fact that concrete processes and concrete production has been a vital, a contributor to the global the carbon emission, and this has been, we cannot overemphasize this. But beyond this, we find out that the growing demand for sustainable construction, it's driving innovative solutions, which is aimed at enhancing both the durability and service life of concrete infrastructures. We will do this through the improvement of the microstructural quality through internal curing. And we found out that internal curing and superabsorbent polymers, also known as SAP, they are very key. They are one of these innovative solutions because they create reservoirs within the concrete infrastructure, which provides additional water to aid hydration. And we've also noticed that the internal curing, it relies on controlled release, gradual controlled release of water within the cementitious matrix, which aids or improves, helps cement hydration and mitigates self-desiccation. And this gives rise to more durable concrete, because we know that durable concrete, the uses of durable concrete, it helps to reduce the maintenance costs, it helps to increase the return on investment, and then most especially, it helps to decrease the frequency of replacement of these structures, of existing structures, and decrease carbon emission. Just a little overview of superabsorbent polymers. They are also SAPs. They are known as hydrogels. They are cross-linked polymers which have the capacity to absorb large volume of fluid in comparison with their own mass, forming insoluble hydrogels. They act as internal reservoirs in the concrete, and then they can also be an alternative to pre-wetted lightweight aggregate for internal curing purposes. From past research, we found out that some of the benefits includes improved hydration. We look at they reduce the moisture gradient in concrete, and most especially, they mitigate certain durability challenges, autogenous shrinkage, drying shrinkage, and scaling resistance. And then also, they help to improve the quality of the microstructure of the concrete. From the past research we did, we found out that we were able to evaluate the absorption capacity of the SAP needed for this project. We were able to also find that when the mixing sequence, the application, because most people ask us, when do we add SAP? When do we add SAP in concrete? We're able to evaluate the mixing sequence. You can scan the code if you're interested in some of the reports we submit, our past reports. We're able to also, some of the questions we also get is that, do we need extra water when adding SAP? Which is also, we're able to find out that even without, you can add SAP without adding extra water. And then we also found out that the effect of extra water on mechanical and properties of the SAP. Also, from the output from the research, we are able to find the comparable, there's a comparable or improved mechanical strength. It reduces autogenous shrinkage and then improves the hydration, as well as increase durability, concrete durability. Now, for the current project, our project goal is to determine how delivery, how we can, because beyond the laboratory experiment, how do we deliver the SAP in the field? So our current project goal is to determine how SAP delivery, and the mixture composition can affect the curing performance of concrete containing commercial SAP formulation, type 1L cement, slag cement, and colloidal nanosilica. So some of the objectives is we evaluated the internal curing performance of concrete containing commercial SAP and slag cement, type 1L cement, and colloidal nanosilica. Secondly, we develop and evaluate the SAP delivery strategies for practical implementation of SAP, in superabsorbent polymers in the field. And then finally, we conducted a field trial where we evaluated the strength and durability properties of concrete containing SAP, and also concrete that we cured with a normal liquid curing compound. For the second objective, how do we deliver SAP in the field? We developed this, we prepackaged SAP in dissolvable bags. These are dissolvable bags. They are water-soluble bags, which we just store them into the mixer. It automatically dissolves. So we're able to prepackage 1 pound of SAP in this bag, and this 1 pound of SAP is equivalent for 1 cubic yard of concrete, and we dosed at 0.2% by the cementitious weight. And this bag was also in order to protect it, it's enclosed in a waterproof bag, so that because it reacts with water, so we enclose in the waterproof bag, which we open, and then you toast the dissolvable bag into the mixer. Why I want to point this out, because the field trial was done in a commercial batching plant, so we needed to find an easy way to batch the SAP. And for the dissolvable bag, we did some laboratory experiment to evaluate the effectiveness of this dissolvable bag in the field. So by that, these are some of the concrete mixing materials we use, and then the mix design for the field, the laboratory experiment we did, we're able to we scaled down the bag because we needed, that was 1 pound bag for 1 cubic yard, but in the lab, we don't need to make one cubic yard of concrete. So we scaled down the dissolvable bag by batching the quantity of SAP we needed. And then we needed, we had 5 mixes where we had the reference mix. Then we added 2 delivery methods for the SAP, directly pouring the SAP and using the dissolvable bag. And also we did 30% of slag replacement, and then also added SAP directly, and then also use the dissolvable bag to be able to see the effectiveness, that the dissolvable bag works effectively before we proceeded for the field trial. And some of the experiments, and from our design, our target slump was between 3 to 5 inches, and then air content was between 5 to 8%. And then for the laboratory experiments, for the mixtures without SAP, we didn't use a high range water reducer, but for mixtures with SAP, in order to improve the workability, we added a high range water reducer at 400 milligram per 100 kg. And then also we also used air in training admixture to be able to meet our target air content of 5 to 8%. We tested for the laboratory experiment. We tested for fresh properties the air content, which is very much important for us, and then the slump. We found out that like for the reference mix, the slump here is at 7 inches, but the addition of SAP, we found a comparable a result from the SAP delivery method using both the dissolvable bag and directly pouring the SAP. And we found out that like the sump is between the direct pouring of SAP was at 4.5 inches, whereas by using dissolvable bag was 5 inches, which is close. And then for the slag, 30% of slag replacement, we had the same slump value and kind of slightly varying air content value. Then we proceeded with the strength characteristics, which we tested compressive strength for 3 days, 7 days, 28 days. And then we also found correlating values between the direct pouring of the SAP and the addition using dissolvable bag. We tested, and then the strength values at 3 days was around 2700 to 3300 psi. 7 days we had 3500 to 4100 psi, and then at 28 days 41 to 500 psi. And we also tested for flexural strength at 28 days. We also had relatable values for the flexural strength at 28 days in the both the SAP delivery method. Further, we also tested for ultrasonic pulse velocity. And then for the pulse velocity, we tested, we found for the direct addition, we tested using beams and cylinders. We found out that the direct addition of SAP, it had a marginal increase at 3, 7, and 28 days, but also we found a kind of increase using the direct the dissolvable bag, which is DB. It's 3%, 4% increase at 28 days, which is also comparable with that of the direct pouring of SAP. The same trend was also observed for the 30% of slag replacement. And with this, we tested for the stiffness, in terms of the stiffness of the mix, where we tested the dynamic elastic modulus. And then we found for both the dissolvable bag and then direct pouring, we had closed values, as can see from the plot. And the same with the dynamics elastic modulus. We tested using 2 types, so we had correlating values. And after this, we now proceeded from the lab to the field. We were able to move where things became more interesting when we proceeded to the field. In the field, this is the concrete mix design we use for the field. This is based on the Indiana Department of Transport Class C concrete, requiring 658 pounds per cubic yard of cement, and then at water to cement ratio of 0.44, and then slag replacement of 30%, and then also we added the SAP at 0.2% by cubic yard by the weight of cement. Here also, since it was batched, the concrete was batched in a commercial batching plant, we didn't use a high-range water reducer at all, and the target slump was between 3 to 7 inches. Target air content was 5 to 8%. And then the mix we had for that, we had six slabs of 8 feet by 8 feet by 10 inches slab. We had a slab number 6, which is a reference slab. We had a slab number 7, that's the addition of nanosilica to the reference slab. Then we had slab number 8, where we replaced 30% of the cement, type 1L cement, using slag cement, and the grade of slag cement we used was grade 100. And then we had slab 9, which the 30% of slag replacement used also by the addition and also adding nanosilica to it. And slab number 10, which is almost the reference mix, 658 pounds per cubic yard of cement, but we added SAP to it. And then slab 11 is replacement of 30% of cement with SAP. This is here is the CAD drawing which we proposed, and then this is the formwork in the field. It was a very cold September morning, so in the field, this is and then we also hired the services of professional concrete finishers for that, to help us finish the concrete, so that we can be able to get a near real life concrete finishing. And the slabs we are cast. And then we also made provisions, we improvised for some cylinders, which we extracted eventually to test for the scaling resistance. And we tested for fresh properties, both the slump and the air content in the field. This is the work of the professional concrete finishers. We ensured that the concrete surfaces we have finished finished to replicate a real life application. And for curing purposes, plastic sheets the slabs we are segmented. Half of it was covered using a plastic sheet, and then the other half was that we applied a liquid curing compound on them. And this is an overview of the slabs we had. We had slab number 6, like I explained. It was a reference slab 7, 8, 9, 10, and 11. And then we also had some beams. We were able to cast some beams to 12 of 6-inch by 6 by 18-inch beam for flexural testing, and then also some prismatic samples for dry shrinkage. And then we also had some cylinders which we transported back into to the laboratory, because we cast them in the field, but we transported back to the laboratory so that to be able to test them in the lab. And also, I need to emphasize that all the slabs we are instrumented using a thermocouple to be able to evaluate the temperature gradients, and some of the Like this is a picture of the thermocouple. We instrumented with thermocouples. And at testing ages of 7, 28, 56, and 90, and 365 days, cores were extracted from the slabs in the field and taken to the lab for testing. And also, we had two curing regimes for this experiment. We had a specimen, the lab curing and the field curing. We had specimens that were cast in the field, but we were taken to the lab, and then at the conditions, we had a constant temperature of 23 degrees, relative humidity of around 50%, and the wet curing. Excuse me. And some of the variables, we had curing, some of these samples, curing compound was applied on them, some were without the curing compound, and then we also had the addition of nanosilica, as well as the samples with SAP. For the field cured experiment, we had a variable temperature, we had a cyclic freezing and thawing, and then the moist condition, and the same variables we also applied. Okay, for the method we used for the testing, we found out that like I said, we tested both for fresh properties, and for fresh properties we tested, and then these are the STM procedures that were used for the testing. And then the specimen specification for the fresh property, we tested fresh concrete for the compressive strength, we tested the cylinders, and then flexural strength, we had 6 by 6 inches by 6 inches by 18 beams. The splitting tensile strength, we extracted cores from the slabs in the field, and they were tested. And then scaling resistance, we also had some cylinders extracted and tested, as well as the resistivity and formation factor. For the scaling resistance, if you notice in during the formwork, we improvised, we created this special cylinder, like 10-inch by 4-inch cylinders, which we extracted. We power washed them to remove the curing compound, and they were diked using a 4% calcium chloride solution, and they were diked and exposed to 50 cycles of freezing and thawing, freezing at minus 18 degrees Celsius for 16 hours, and then thawing at 4 degrees Celsius for 8 hours. The icing solution was removed after every 5th cycle. At the end of 50 cycles, we evaluated both the mass loss, and we used visual inspection and then mass loss to evaluate that. And then for the depth of chloride penetration, the slabs in the field were also cleaned and diked, using calcium chloride, 4% of calcium chloride. And at the end of after 28 days of casting, they were diked, and the solution was left for 150 days. At the end of 150 days, we extracted cores from those diked portion, and after splitting them, we applied silver nitrate to evaluate the depth of chloride penetration. The same for rate of water absorption. Also, we tested both for the cores extracted from the field and the cast ones that were cured in the lab. So at this point, we'll proceed to talk about some of the results we obtained. First of all, on fresh properties, we noticed the addition of SAP. There was a decrease. It reduced there was a reduction in the slump value, in the workability. But the addition of SAP, the slab number 11 that had slag in it, it also compensated. The addition of SAP helped to compensate for the reduction in the workability. But I also need to emphasize that all the mixes met our target air content and target slump. So. These are some of the pictures of the mixes when they were cast. The addition of SAP, the middle picture, you notice it became a little bit stiff, and but for the professional guys that were finishing the concrete, they didn't want to finish it because they don't want to spend more time trying to finish concrete. So most of them had their own reservation. But the addition of when we included slag, it improved the workability of the mix. And then for flexural strength, the beams we are tested at 4 days. We are looking at how early can we open this pavement to traffic. So we tested at 4 days, and these are some of the results we obtained at 4 days. The range of results was between 400 psi to 550 psi for flexural strength at 4 days. And then the requirement, the Indiana Department of Transport standard specification for modulus of rupture at 7 days was at 570 psi. psi, and then that's for structural concrete. And then also they made provision for concrete patches for pavement, for bridge decks at 550 psi at 3 days. And we found out that the addition of SAP, the addition of SAP helped to improve the flexural strength. And also, if you notice the third bar, the mix with 30% of slag reduction had a reduced flexural strength, but when we added SAP to it, it also improved the flexural strength. So there's a synergistic effect between SAP and slag in improving the flexural strength, especially at early age. So it's compensated for the reduction in the early age strength reduction. Compressive strength, we tested for 7 days, 28 days, 56, 90 days, and 365 days. And then we had some result both for the specimen that we are cured in the lab, at the lab cured specimen that's controlled condition, and the scores extracted from the field. And we also noticed that there was a gradual increase in compressive strength with age, but there was for the mix with slag, there's a slight reduction in early age strength, and also we noticed an increase as the age of the concrete increases. So the latent hydraulic property of slag came into effect, especially at a later age. But the addition of SAP, if you notice the third bar, the addition of the last bar, the addition of SAP helps also to compensate for the loss in early age strength for the mix with slag and SAP. So the similar trend was also observed for the mixes with slag, for the cores extracted from the field. And this is also very interesting plot. We try to compare the effects of different curing conditions. The first plot, we had the non-curing, the slabs without a curing compound. The second plot, the second bar is we had applied the slab with a curing compound, and then with the addition of nanosilica, and then with addition of SAP. And we noticed the gradual increase across all age, both 7 days, 56 days, 90 days, across all age. We noticed an increase with the addition of SAP, so showing the internal curing performance of SAP in concrete. For splitting tensile strength, we tested at 180 days, and also we had similar trend as we observed with the compressive strength, a slight reduction in. And since we tested at 180 days, the mixture with slag also, there was an improve in the tensile strength, as well as the combination of SAP and slag. And this we also try to evaluate the temperature, the temperature gradient for the thermocouples that were instrumented in the slabs. And for that, we noticed the addition of 30% slag replacement also reduced we saw a reduction in the core temperature from almost 44 degrees Celsius, to 37 degrees Celsius. And even the addition of SAP also further reduced the core temperature by the addition of SAP and slag. Then, moving forward, we look at some of the results we have from the durability results for the scaling resistance at the end of 50 cycles using visual inspection, and we found out that there was no mass loss, and there was no mass loss, and then also the visual rating was 0 for the slabs, and the depth of chloride penetration. At the end of the application of silver nitrate on the cores, we noticed the addition of SAP, 30% of slag replacement helps to refine the microstructure, leading to the reduction in the depth of chloride penetration. And the SAP, it also compensated for SAP because SAP introduced a kind of voids in the mix, but the addition of SAP and slag also helped to reduce the kind of refine the microstructure, reducing the depth of chloride penetration for the mixes. And for our initial absorption, for water absorption, we noticed a gradual reduction. We noticed a reduction in both initial and final water absorption by the addition of slag, 30% of slag cement in the mix. And finally, we'll look at the resistivity, which correlates with both the depth of chloride penetration. We noticed the addition of SAP, increases the resistivity, the resistivity, and the formation factor for the mixes, which it shows the refinement of the microstructure, and then also improvements, both improvements in the. It helps to a reduction in the permeability, and which translates to higher durability for the concrete mixes. Now, in summary, we found out that the use of, first of all, the use of dissolvable bag was very much effective for SAP delivery in the field, achieving adequate dispersion and mixture consistency. Secondly, we also found that the early age, the addition of SAP, and slag helps to improve the early age performance of mixes, which when we compare the SAP-free mix with the mix with SAP, so it helps to improve the early age reduction, which is associated with some slag mixes. And then also, when compared with the surface curing of like application of surface curing compound, we found out that SAP significantly improved the compressive strength and then from both the field cast and the cores, because we are across all ages. And then we also found out that the mixtures containing both SAP and slag, they displayed both reduced chloride penetration depth, when we compare with the SAP only mixes. So this shows a synergistic effect together, helps to reduce the permeability and enhance both the resistance to chloride penetration. Finally, we found out that concrete mixes containing slag shows higher resistivity, as well as low chloride permeability. Thank you very much. This is our project team, and I want to appreciate both the Indiana Department of Transport, the Joint Transportation and Research Program, and especially Slag Cement Association for this wonderful opportunity. And finally, but not the least, I want to appreciate Purdue University for the opportunity to be here. Thank you very much.